Today we are going to do section, 4.4, I believe. So let's first scan the book. It has gotten wrinkled there. All right, here we go. This is the first page, which happened to be a brand new page, I guess. Okay, let's see. And then a little closer. And then on the bottom. Okay. All right, and next, this is page 134 and 135. All right, so we have that. And then let's zoom in on top a little bit. And bottom. Let's see. All right. Okay. Now, before we start, I want to remind you some of the determinant rules that we'll need in this section. First, when you have two matrices, okay, A and B, the determinant of A times determinant of B is the same as the determinant A times B. Okay, I mean, that is, you multiply the matrix first and then calculate the determinant. Before or after is the same thing. And this is something I've shown you before. What is a cofactor? Okay, here's the definition of cofactor. Specifically, the cofactor of AA is equal to the determinant of that other thing, which the other side, the little one, okay? And the determinant of this thing plus multiplied by some kind of a negative one, depending on whether A11 is positive or negative. And here's the exact formula for it. And remember what a minor is. So the cofactor is the determinant of the minor, okay? And next, I want to remind you that when you add multiples of one row to another row, then if you were to do that, then the determinant doesn't change. And yeah, so that and that applies to column as well. So that is that's a couple of old determinant rules I want you to bear in mind. Now, having said that, let's I guess we can start looking at this. First, please read the first paragraph of we are now on page 132. Okay, this is not zooming in. Okay, so I think it's okay now. So please read this paragraph by yourself, and we are going to continue, and I will talk about quadratic forms. The quadratic forms, well, as it shows here, is a bunch of stuff where you have two variables, x and y, and it forms something that looks a bit like determinant, where things, when x is kind of, well, okay, so there is the two variables are actually it's not two variables, it's just one variable. There's x1, x2, and x3. So I guess total of three variables. Yeah, it says so. Why did I say two? I mean three. But two of them are being multiplied at a time. So we have, as a result, this interesting structure where the functions of three variables, and each variable either multiplied by itself or multiplied by some other thing, okay? And you end up with nine terms. In reality, remember the 9 terms are just for aesthetic's sake, because look at the middle of the page, on the other side of this finger, okay, where it says Aij equal to Aji. That's important because in reality, x21 is the same as x12. So this part, the bottom part, can theoretically be eliminated, and whereas this part would just have, two of those, or just have the coefficients being twice as big. However, we write it this way because then it looks like a determinant of a matrix. The coefficients do, and that does come with certain benefits. And then, although other times it might make things unnecessarily longer than it should be. In any case, so this function, okay, this interesting function of three variables, right, is called, excuse me, is called positive definite if the function is bigger than 0 for any value of x1, x2, x3, except for when all three variables are 0. Because when all three variables are 0, then of course the function is 0. But the question is, well, anytime when the three variables are not all 0 at the same time, whether they are positive or negative, the function just happened to be positive because of the way the coefficients work. Now, if that is the case, then we give it a name. It's called positive definite. Now, if it is if the function has a quality that it is either positive, but it is 0 at values other than the origin, x1, x2, x3 equal to 0, then, but it's still positive, that is, its values are either positive or 0, then we'll, but it's 0 beyond just at the origin at 0, 0, 0, then we'll call it positive semi-definite. Okay. So as an example, then we look at the function f, which is x1 squared, x2 squared, and x3 squared, and you can see why this thing is positive definite, okay? Anytime, as long as the three variables are not all 0 together, this thing is going to be positive. And similarly, the function g is going to be positive all the time, or 0. When x1 and x2 are both 0 for function g, then doesn't matter what x3 is going to be 0, right? So it's 0 along the line where x3 equal to 0. And so it's 0 more than one spot, and therefore it's positive semi-definite. Now, however, if you restrict g and look at it as a function of only two variables, that is, you don't think about it as a z component and like it doesn't exist, in that case, it would be positive definite in the two dimension, right? And so and negative definite forms are defined in a similar way, okay? And there's actually a word here for it. It's called, the book calls it, in a similar way, throw in a Latin form here. That is, this is mutatis mutandis. And old books like to throw in Latin once in a while because students used to be forced to learn Latin in school, whether you need it or not. So that's why. I thought I wrote it down. What does mutatis mutandis mean? Maybe I didn't. Let me check. Well, I can't seem to find it. I thought I wrote it down. It means changing proper things that need to be changed. That's the mutatis is similar to the English word mutate or something. Change something that should be changed so that the negative definite form is defined in a similar way. So then the next statement we have is that in two variables, this thing right here, okay, this is the quadratic form in two variables. And this is positive definite if a is bigger than 0 and AC, and this particular determinant, AC minus B squared, is bigger than 0. Now, you may or may not have had that before, but it's very easy to prove. Well, I don't know about easy, but it's very short. The proof is short, and it's how you might imagine. What happens is, to show this thing is bigger than 0, as with those conditions of A is bigger than 0, right? And this particular, and the determinant is 0. What we're going to do is this equation will hold x2 be a constant value that isn't 0. If it's 0, I think is even simpler. But yeah, so if x2 is not 0, then then we can then this whole thing becomes a quadratic equation, right? So then we will, if it's a quadratic equation with x1 being the variable, then it looks something like that. And we need this thing to be positive definite. So this thing needs to be so this thing needs to be we need the what is that? That is the stuff under the square root in the quadratic formula to be less than 0. And that way there's no real roots. All right. So that is, in other words, is on top of above the x-axis. So that situation then, of course, becomes b squared minus ac is less than 0, or put it another way, AC minus B squared is bigger than 0. And then, of course, A has to be bigger than 0 so that we're positive definite. So that two conditions, you can see quickly why that would cause the function to be positive definite. So that's for the 2D. The 2D situation is easy enough to consider. And so now let's consider the 3D, not 3D, but 3 variables. Okay, now we're thinking about 3 variables, which is sort of 3D either way. So to prove, and we're going to find the situation where the 3D is going to be positive definite. And as you can see, it follows a pattern. Let's look at lemma 4 at the bottom of the page. We have A11 is bigger than 0, just like this one, okay, the first variable. And then the next determinant, the 2 by 2 determinant, is also very similar, and where the A's follow this pattern right here, this definition right here. And then, but there's a third one, okay, for the 3 variables, we need the third determinant in the order that's presented to be bigger than 0, which is one reason we write the quadratic form this way. Okay, then we can write out the determinant. And as always, remember the mixed things are the same. That is, A21, for example, is equal to A12. We just write it this way so that the determinant is easier to see. Now, to prove lemma 2, you need to get ready for a bunch of patient manipulation of determinants. What are the matrix determinants? Okay, so we're going to pull some trick here. Now, first, the goal is that we're going to prove this. We need to these are the cofactors. Okay, remember what the cofactors are. Now, the cofactors, well, first let's say how are they defined. Let's see here, down here. No, wrong one. Over here. Oops. Okay, the cofactors are defined as the cofactor of AI, small ai, is defined, we'll call it big AI. So the cofactor of A11 is the determinant of these 4 things right here, okay? And that sort of thing. And anyway, so again, please review what a cofactor is if you already forgot. But I mentioned it in the beginning of the video, and you can also look it up, of course. The point is, so those are cofactors, and we're gonna, in order to prove this backpacker cofactor. Now remember, each one is a cofactor, so there's a little 2 by 2 determinant in each of these things, okay? Which sounds like a lot of algebra you're doing, and it really is. But if you but this is what we're trying to prove. Whereas the triangle is the determinant of the 3 by 3 thing. Okay, this is called the triangle. Does it say that here? Yeah, it does. See, the 3 by 3 determinant, it will be called the triangle. That is delta. I'm just going to call it the triangle because it sounds nicer to me. Anyway, so here's what we're striving for. Okay, we're going to prove somehow that this determinant, where each one inside here is a determinant, a little determinant itself, a 2 by 2, and this 2 by 2 determinant is equal to A11 times delta, where delta, or triangle, which triangle is this thing. Now to do that, the book is going to pull this trick. We're going to take triangle, okay, times this particular determinant, and then it end up being this. And well, why does it end up being this? Well, I can think of no good way to show that that's true by just going through the work, which is what I did. But I didn't do all of them. I think, okay, here's multiplication. Remember, determinant A times determinant B. You can multiply them together first, then calculate the determinant, right? Whereas Aij is the cofactor of small aij. So you multiply that times that, and that's the first step, okay? Then you have what? About 6 things, and that has to equal to this other thing. I wrote it out, okay? The question is, does that equal to this? All right, and yeah, I think the first row is okay. That came out pretty good. The first row is pretty obvious. The question is, what happened to the, so here is my first row. I wrote it, across multiplied down, so I wrote it this way. The book wrote it across, the same thing, okay? Because the determinant of transpose matrices are the same. So you can write a column or rows, if they are, the determinant end up being the same. So anyway, so the first column is fine, or row is fine. The question is, does this end up being whatever the book said? And it does if you work on it. Now, I worked on two of them. I worked on A12, okay, and then again on A22. And after doing some manipulation, you notice I think two of the terms cancel out, so you end up with just two terms left, and it does equal to whatever it is that the book says equal to. So I did two of them, and then I was tired and didn't do any more. So please get yourself, try to do as many as you can, okay, to confirm that this is correct. Of course, it does follow some kind of a pattern, and so it does work out this way. Now you notice that if there is any kind of pattern, what about this one? Where did the triangle come from? Even if you work it out, it still might not look like this, because there's yet a next step. Let's see, what do I have here? Well, anyway, so then continuing, you have we have this thing written out, okay, but there's no triangle in it, really, even when it equals to the other thing, because everything looks sort of similar, right? So the answer to make the triangle appear, what we're going to do is pull that trick where we're going to add multiples of one row to another row, because when you do that, then the determinant doesn't change. So we're going to add A21 times this, the first row. This is the first row, right? Yeah, this is the first row. So we'll multiply it by A21 and then add it to the second row, which that actually just end up being this. That makes everything go to 0. So what I said earlier about why the other thing is the same, well, it just does, okay? I mean, if you confirm it, yeah, it somehow there's it does equal to the triangle A22. Yeah, I did confirm that A22 equal to this thing, which end up equal to the triangle minus A12, okay? So this is that, and well, anyway, it's a bunch of messy algebra about determinants that if you work on it, it will all come out. So that's how the triangle works. In the meantime, so the next step, what I was doing is getting to the next point. We need to knock everything. This has to become this, okay? So the first row stays the same, but the second row magically becomes triangle in the middle and the last one, and the rest becomes 0, which would be very nice if that was the case. That makes life much easier, and that is what I was talking about, is we're going to multiply this value of A21 times the first row and add it to the second row, and if you do, that will end up being 0, triangle 0. And similarly, adding A31 times that times the first row and then add it to the third row will force the third row to look like that. And so then eventually, so what is that? That is the same as A11 triangle squared if you multiply the determinant out. Okay, so all that sounds like a lot of trouble. And what have we been doing? You see, by now you might forget what are we doing to start with. So we got to here, okay, after a ton of algebra. So what happens is this big determinant is the same as this small one, all right? So basically what we got is triangle times this thing equal to, triangle times this thing is equal to A11 triangle squared, okay? So we divide out one triangle, and so we end up with this determinant, which is the same as this one, is just A11 times triangle, and that's what we've been striving for, doing all that stuff. Okay, now why did the book choose to do this? Off the top of my head, I can't see it myself. You know, I mean, it's not obvious to me where this come from that he was able to drive at this point. So it's just a cool trick that the book pulled in order to prove that this relationship is true. All right, so so we got to this, in any case, we got here, okay? And that we're going to need this in order to prove that, well, what are we doing again? We're proving lemma 4, where we're proving the sufficient condition. That is, if these conditions are true, then the form F is positive definite, okay? So, so these are sufficient conditions, in other words. Okay, so let's continue right here. The next step we're going to do is collect terms in this equation. That is, we're going to treat this thing like x1 is the only variable and everything else is a constant, okay? Which you can do. So we'll put A, by the time you collect the variables, you will notice that the big A is just small a11, so far so good, okay? And then you collect all terms that has just x1 in it, and all the stuff attached to it will be called 2B, and you will realize that B will be equal to this thing. And similarly, whatever's left, okay, that doesn't have x1 in it, we'll call it C, where C will be equal to this thing. And so please work that out yourself as well. There's a bunch of algebra. I think I did that. See, right here, I wrote a bunch of stuff down and then calculate, yeah, and then I collected the terms and I did come up with all these things, I guess. All right, so far so good. So what we have right now is a certain quadratic form. In other words, this thing, we are going to use, what we have? Yeah, we're going to use this thing, okay? And then use this condition to prove that this thing is positive definite. So we're going to use this relationship right here. All right, so let's see the other side of the book. We have, so now we have this thing out, and we're striving to show AC minus B squared equal to is bigger than 0, which will prove, that will prove it, okay? Because like the quadratic form on the previous page. Now to do that, then of course, if x2 equal to x3 equal to 0, that's not a concern, okay? And so then how do we? So the next step is we're going to prove AC minus B squared, and calculate what that is. And then after much algebra, let's see what I did. Okay, so that's what I did here. Please do this yourself as well. So calculate what AC minus B squared is. Equal to this pile of stuff, which happens to be A33 x squared minus A32 x2 x3 and so on. And A22 x. After you get all the algebra to come out, okay? So being the A33 happens to be this thing, which is given as bigger than 0. Okay? Because that's the that's the second inequality. Okay, this thing right here, this is A33. All right, so we have where am I? A33 is which is, and the first coefficient is bigger than 0, and then by the by the quadratic form rules, okay, this thing, which is equal to A11 times triangle, which we have proven that A11, this thing is, if it's a quadratic form, then this thing, which is the rules here, okay, from quadratic form, is going to be bigger than 0. And which proves that the triangle is, no, what am I, let me pay attention. That being the A11 is bigger than 0, the triangle is given as bigger than 0, then this relationship is bigger than 0, which means AC minus B squared is bigger than 0, and therefore the form is positive definite. Now that is that concludes the proof of lemma 4. Now that all sounds like a ton of work to prove something that isn't really a real theorem. A lemma means inferior or small little theorem. I think the hardest part is getting through this part, okay? And but you might think, why can't we just do this, right? I mean, that's what I thought. So I did that. I mean, I just went ahead and, forget all the other stuff and just go right. Let's prove that thing, okay? how about we just prove this thing the hard, like the brute force way. We know what all these big A's are. Let's just plug it in and see if it equals to that thing. So I did that, and things can't subtracted, stuff canceled out, or something, did it cancel? I don't know. But anyway, so yeah, things are term for term, and then I multiply A11 times the 3 by 3 determinant. Things do turn by turn checks out, see? And that didn't take near as much work. So it seems faster if we just simply do this. But anyway, yeah, and then the rest. Anyway, the rest of the terms either cancel themselves, okay, or they equal to this. Anyway, that this shows that this thing does equal to that, okay? And you can look at that if you want, but I'm not going to go into it. It's just please do that yourself as well. This is much easier than what it did before. Now, so I'm not sure why the book go through the hard way, but it is neat, okay? The book did some kind of a magic trick, and everything seems to come out beautifully. It just seems it's still rather tedious. It's hard to say which math is easier. But anyway, so in any case, the author is able to drive, after much manipulation, able to drive to this point, which is impressive, because I wouldn't know how to, or even to get there, let alone how to get there. Well, anyway, so either way, that is how lemma 4 is proved, and which is quite tedious. But please do this yourself. At least do part of it, okay? To confirm that all algebra terms turns out properly like it's supposed to. So that is lemma 4, which will be important for us in the in the following proof. Next, let's read the bottom of page 133. Okay, there's a difference between the form in 2 variable and the form in 3 variable, and the difference is the former is if you want to change it to positive semi-definite, what you're gonna do is you're gonna put this is for positive definite, right? To be semi-definite, you just change this determinant to be bigger than or equal to 0. That will make it semi-definite. Now, if, however, but not the first one, still the A still need to be bigger than 0, because then you still need to be positive. And so, however, if in the 3-dimension case, if you want something to be positive definite, you will need to have the 2 determinants to be bigger than these 2 conditions, to be bigger than or equal to 0. However, that is not good enough. That's not sufficient to show that something is positive definite, semi-definite. And the reason for that, well, it's not the reason, it's just an example, okay? And let's say let's look at the example here, okay? Because in the case where, such as this function, if we put the second and the third determinants to be 0, as is true for this example, please verify that quickly, okay? That should be pretty easy. It's a very simple example, so it should be easy to verify. In this example, all the A's here are 1 except for A3, which A33, which is 0 because it got subtracted out. So when you know, then as a result, both determinants are 0, but the function is negative at a certain point, which means this function is not positive definite. So that is only is a necessary but not sufficient condition to have the 2 determinants equal to 0 to prove to ensure that your function is semi-definite. It's just a comment, yeah, that one might bear in mind or notice. We are not going to use that in the homework, though, that I noticed. So anyway, let's move on to the next page, where we'll look at theorem 4. Theorem 4, which is what we did all the whole bit about quadratic form and lemma 4 and all those giant massive algebra, that's what we did it for, okay? And now that we got through all the grunt work, our life is going to look much fancier. Now, let's read theorem 4. The function is C2, okay, with continuous second order partial derivatives, and it is the first derivatives are all 0, okay, so there is a spot where things goes level. The question is this some kind of a relative maximum or minimum? And now, if the condition is satisfied, statement hypothesis 3, where f11 is 0, and then the small determinant is 0, okay, and then the big determinant is 0. If all three conditions are satisfied, then the function f will have a relative minimum. Now remember, relative minimum means it's smaller than everything around it, okay? It's different from the definition of absolute minimum, where it can be the same and equal to the something around. Relative minimum, it cannot even be equal. It's absolutely the smallest thing in the small neighborhood. So then how are we going to prove that? Well, in a similar case as we did before, we're going to have Taylor's theorem, which is we're going to do the same thing as page 127, where we had the Taylor's theorem explained, end up being like this, being that the first derivatives are all 0. Okay, so in a similar manner on page 127, except that on 127 that's 2 variables. Now we go up to 3 variables, so we end up having something like this. But the idea is the same. Okay, we have this thing where where I'm not going to write this out because we'll just go for that. Okay, so by Taylor's theorem, then so far we got that part. And then, so by hypothesis 1, which states that the function is continuous, has continuous second derivatives, all the in some neighborhood, okay, of x, y, z, which means that this. All the inequalities in hypothesis 3, see, all these situations all apply in some neighborhood of x, y, z, okay, and because every partial derivative here is continuous, so then they must be So then the inequalities has to hold, okay? Because it holds at one point, it must hold at some neighborhood of the said point. All right. So if that is the case, then this point, okay, x, when you move the point a little bit to h1 to this new point, then it is, as long as the new point is in that neighborhood, the coefficients will satisfy the conditions of lemma 4. That is, the coefficients will be, being that they're all bigger than 0, those 3 things, okay, they look identical to lemma 4. What that proves is by lemma 4, then the function, which in this case is delta f, is positive definite. Now, how cool is that? So suddenly we can say then in this case the function is delta f is positive definite, which means it's bigger than 0 throughout the neighborhood except where at its original point, okay, where h1, h2, and h3 is 0. Because there the delta f is just 0, but because delta f is the change of f, okay, from the original point. So at the original point, of course, there's no change, but everywhere else in the entire open neighborhood, the delta f is going to be bigger than 0. Now, what does that mean? That means it has a relative minimum, okay, a local minimum at the point x, y, z, and we have proved our theorem. So lemma 4 is basically the strong force that pushed this theorem right to the end, okay, with one punch, and basically knocked it out with one punch. Now for a relative maximum, now this is for relative minimum. Now what happens with relative maximum? For relative maximum, only the first and the third of the inequalities need to be reversed. The second inequality does not reverse. That is, the odd inequalities, you know, the one that has one term, this is a 2 by 2, the 3 by 3 term, this one and this one has to flip over to calculate the relative max. Now, why is that? You just, if you imagine that the function is, to calculate the relative max, you're just calculating the relative min of the negative value. Right? For example, if you let g xyz equal to negative f of xyz, then whatever is the relative min of this thing is, well, then the relative min of this is the relative max of that, you know, because the thing is just flipped. At least the location is. Is at the same spot. Now to do that, then we apply that function, okay? And then you notice that the g's are all negatives. Everything is negative of the other one. As a result, the even determinants, the 2, 1, is going to be the same as the other one, whereas the odd ones, okay, being that you have negative 1 3 times, then it becomes negative. So the 3 by 3 determinant is going to be less than 0, and then whereas the 2 by 2 determinant is going to be bigger than 0, which is that is why the this is important, okay? And for relative max, the first and third of the inequalities in hypothesis 3 you're going to need to be reverse inequality. The second one doesn't, because the negative signs canceled out when it's 2 by 2. So please work that out yourself, you know, and yeah, it's a pretty pretty straightforward if you stare at this for a little bit, or write it out yourself and see why that is the case. Okay, so next let's look at example A. Example A is a straightforward application of theorem 4, for which to do that you just have to calculate out every single f11, f22, etc. But this example happened to be nicely designed or easily designed, so it doesn't work. So we're not too worn out by calculating all that stuff. So I did all that here. Okay, f11, f21, f1, f2, etc., etc. And so, so as you can see, this end up being a relative min. So please do that yourself as well. All right, and with that we have come to the end of this section. For homework. Please do problems, every problem except problem 3, which is, yeah. And okay, let's see, let me show it to you. Where's the homework? Right here. Okay, so please do every problem except for problem 3, which is 1, 2, 4, 5, 6, 7, 8, 9, 10. Now, I want to warn you that problem 5 and problem 10, I find them to be quite tedious. Okay, so if you're working on it and you feel like you're worn out, don't hesitate to use the calculators, which is what I did. But for both problem 5 and problem 10, I was there was so much algebra. I ended up pulling out various calculators and to get them through. And one more thing I should mention, that problem 5 talks about a wall tent. A wall tent looks like this, okay? And yeah, so in case you wonder what a wall tent is, like a little hut and with flat sides on both sides. And so please go do your homework. And, and when you're done, I want to talk about them. So let's look at problem 1. Let's see, where is it? Let me find my notebook. So problem 1 is problem 1, okay, right here, which is similar to the example in the book. Okay, we just have a bunch of stuff. We need to apply theorem 4, which means we have to calculate all the various things, f1, f2, f3, and then all the partial derivatives on the other side, and then plug in x. We're calculating as the origin, which make things a bit easier. So let's calculate the f11, okay, and then the 2 by 2 determinant, and then the 3 by 3 determinant, which everything works out in the opposite way. That is, this inequality stays the same as I mentioned before, but this one and this one flipped to be less than 0, and in which case by theorem 4, in the adjusted theorem for relative max, f has a relative max at the origin. Okay, so so next, let's consider problem 2, where the coefficient of x squared in the function on top now becomes positive. So what happens then? What happens then is then we quickly find out that f11 is okay, but this thing then becomes negative 12 and is less than 0. And the theorem 4 requires the second, the 2 by 2 determinant to be bigger than 0 to work, whether it's for maximum or minimum. Okay, so we cannot apply it. So as a result, we still need to know what that thing looks like. So what we're going to do is consider what happens when this at fxy equal to, and z equal to 0, and just to check it. Now, so at that point, we consider this as a 2D situation with just x and y variables, and we find out quickly by the previous theorem that this determinant right here equals is a positive number, which by the previous section, that means f is a saddle point. Okay, if it's a saddle point in 2D, that means it's also a saddle point in 3D. And with two variables, it means that the delta f also is sometimes positive, sometimes negative. So which means in 3D is also some kind of a set. Well, we haven't defined what a saddle point even is in 3D, but the point is something similar to a saddle point where it's sometimes positive, sometimes negative, and therefore it is not some kind of a relative maximum or minimum. So that is problem 2. And then next, let's consider problem 4, which is a throwback, I guess, of a previous section. So before, we were doing a curve that's y equal to a plus bx, which is a straight line. Now we draw a line across a bunch of points in such a way that the line is close to all of them as much as, yeah. So then now we're going to not draw a straight line, but some kind of parabola, okay, and with x squared. But we'll do the same trick. And basically, so we're going to apply the same trick, which is a bunch of writing, okay. We have copying from page 130, we'll do exactly the same thing. So there's f, we have f1, f2, f3, all equal calculated, and they all have to go to 0, which means, which when you clean this thing up a little bit, then you get 3 equations, right? The equations are linear because we're solving for a, b, and c. Yeah, once we solve for a, b, c, we know our equation of the line, and then we know, yeah, we know that's what we're looking for, right? The equation of our parabola. So so all this stuff, and that is the equation of A, okay, divided by this other stuff. And then, so now that we have, there's A and B and C. So now that we have the equation, which is a bunch of stuff that's being summed up and calculate determinants, now, so we can figure out what the points are. The points are, there's some points given to us, right? And we're supposed to plot our graph, which is what I did on the Desmos 2D calculator. But first, we have to calculate all that stuff. What is, x, let's see, okay, see, the x fourth to the power fourth, 3 and 2, and x squared times y. Okay, I have each one of those calculated. And then, yeah, and then summed all up, okay, over here. This is the spreadsheet, which I used the spreadsheet to calculate all that stuff. Let me see, I don't even understand. What does that mean? Let me look at it. Okay, what I mean here is these are the x value of our 4 points, okay? And x value raised to the power 4. Over there is the y value of our 4 points. And I have 0 on the last row. Ignore the zeros, okay? They don't mean anything because we only have 4 points. And we need to know the x power 4 of each, the 4 points, etc. And that's not all. And we need to also know the sum of value x, etc. Okay, all this stuff. So I got it all typed out, and then I made some mistakes and couldn't get the right answer and had to hunt down my mistakes and eventually got it. Okay, so once I got the right answer, there is these are the points. I have some of the points in here. The other points are on top. I didn't bother showing you. So anyway, the points are plotted, and as you can see, this is the graph that I came up with after doing all those sums. Okay, so I calculated what A, B, and C are, and that's the determinant. And anyway, so once plotted, then Desmos drew me a very nice line that looks pretty good. But this book does this quest problem does have an answer. This is the answer of the book, and it is identical to this one. Okay, if you turn this graph on by checking this button, then you notice that the two graphs coincide. So that is the right answer. After I made, I don't know, at least a couple of mistakes and had to hunt for it, which was a real pain, but overall it wasn't bad. Okay, I was able to find the mistakes. Kind of. Anyway, so that is that. Hopefully you didn't make any mistakes, so you don't have to waste time like I did. Okay, so next, problem 5. All right, now problem 5, we're calculating some kind of wall tent. Well, I downloaded a picture of a wall tent to show you. I mean, you can just look at it yourself, of course, but I thought it looks kind of nice. Okay, I'm a big fan of tents. Although I think I also own a wall tent. Yeah. Then anyway, so that is a wall tent. Next, we need to calculate the area, maximize the volume of the wall tent. The formula of it is obvious enough, right? And this is how I did it. So I set the width of the wall tent to be 2x. Well, anyway, so there's 2x and there's y, and then the depth is z, and that sort of thing. And so as a result, I come up and then I pulled y out to plug into the rest of it. Okay, so I got some kind of formula like that. And then and that thing looks kind of a pain to me to take the partial derivative off. So, but I did do the with respect to h, because that looks like the easiest one, and it is. And from partial v partial h, I was able to get the x this relationship out. That is x equal to square root 3 of h. Okay, from here. So as a result, which means if that's the case, then the theta on top, the angle of the roof, has to be 120 degrees. So yeah, so far so good. But then I, of course, have to take the partial derivatives with respect to x and z. And I wasn't gonna, well, I think I kind of tried, and then I couldn't go on. It was just so tedious. So what I did is pull out the Desmos calculator. Or some not Desmos, the Wolfram calculator. So I typed it into the calculator. I will remember to also put the link of the partial derivative calculator in the video description below. So I typed this thing into the formula of the volume into the calculator with y in there. Okay, and so that is what it ended up being. Where I choose the A, the total area, I set it at 100 because so that it doesn't get stuck with yet another variable. And also I feel like 100 is pretty easy to track, right? If you see 100, then you know that must be A. Yeah, and also I put y equal to h, because the calculator wasn't happy with h, okay? So it was okay with y. So y equal to h in here. Please remember that. And so once I got that in, the Wolfram calculator is extremely impressive, okay? Then it cranked the whole thing out. What is this? There's a derivative with respect to x, okay? Y is h, okay? And that did work out to be exactly what I got, so that's good. And then partial with respect to z. So that totally helped me because, yeah, otherwise I was so stuck in the grunt work I was never going to get out of it. Yeah, so once I got that, so the partial derivatives looks quite scary still, but remember I already figured these relationships out. That is x squared plus h squared happen to be 2h, and x equal to square root 3 of h. And in the partial derivatives, I have remembered the equation. So I substituted in here for x and partial z. So that made it quite a bit better, okay? And then life. Once I know, remember in these things, y stands for h, okay? And then, so once I did that, then I was able to reduce everything into two much better looking simultaneous equations that I am somehow not finding it. I'll find it. Yeah, I think it's on the next page. I found it. Okay. So I end up with partial v partial z. Just after it's cleaned up, this is not the whole partial derivative, but after it's cleaned up and set to 0, then I got these two equations, which look pretty good until you look at it more carefully and realize that it is a giant pain, okay? So what I did is that I plugged in these two equations into the systems of equations calculator, which Wolfram also has. I'm telling you, the Wolfram calculator is extremely impressive. So let me find it for you. So I had Wolfram calculate this for me because I was so tired by then. I was not about to do some systems equations that has a radical in there. So anyway, so I typed it in here, both equations, and remember to separate them with a semicolon. Okay, I wrote it down here. And in this equation, I set a equals to 101 because when I put a as 100, then it got, I don't know, factored out or something. I couldn't find it. So putting a as 101 works out much nicer. So the calculator says to solve these two equations, okay, and then it gave me a bunch of values. We'll ignore all the complex values, and then look at the positive, ignore the negative values. So here's the positive values, and this does work out, which is very, very nice. Okay, the y equal to this thing, and z equal to that thing, and when you then when I plugged it in, everything does work out. In fact, to even plug it in, it looks like a lot of work. So, because in order to plug it in, what did I get? Okay, so I got okay, so I got z equals to anyway, I plugged it into the simplify calculator, which I also have, okay, in systems equation. Do I have the simplify? Let's see. Give me a no, I forgot to put in the simplify. I'll get it in. So I have once I got here, then in order to calculate this value here, what was this anyway? Anyway, we have to plug things in. That is equal to h. I think I had to somehow plug in the y equation or something. Yeah, I had to calculate y. It's either y or h. I did a subtract. The answer didn't look identical to y equals to h, okay? But the answer didn't look identical, so I just did a subtract minus sign here. There's a very short minus sign. And it does equal to 0, which means these two equations are identical. And so here a is again 101, so that this thing can do the math properly. And well, yeah, that's following the equation for y. Anyway, so that is well, I'll show you the rest of it. Let you decode the rest of it. Okay, that is just the. It's still really, really painful. Oh yeah, this is what I use the simplify calculator for. Y equal to this thing, right? We have to plug in both x and z, and to eventually figure out the y equal to h, which is that thing. Yeah, which is what I did here. I should mention that to type it into the simplify calculator, you notice that there's a ton of stuff. But in reality, this is all the same. See, the ones I marked as blue are identical, so I just copy and pasted it in there. So I only had to type it one time, okay? And then the rest all come out nicely. So you don't have to work as hard as it looks. But still, it's anyway. Yeah, so eventually I figured out the answer. And what is the answer? The answer is the y value equal to h, okay? The dimensions, okay? The y value, which was like the height of the rectangle, is equal to h. X value is equal to z is value equal to 2x, which means the bottom is a square. And then and then yeah, and then everything is equal to whatever it is equal to. Okay, this is the value of y, and value of h. Where's value of h? It's somewhere. And then value of x, and yeah, h is right here. And value of z, and value of x, and anyway, I'm done. It took me a very long time to do this problem because I'm stuck in so many grunt work that I'm not good at. Because I make so many mistakes. So I was never sure like if I got the right answer or not. And then so that becomes really frustrating, and which is why the calculator is the lifesaver. Next, let's look at problem 6. Now, problem 6 is identical to the example on page 124 and 125, okay? So I just flipped to that page and basically copied everything like it says. And so we take the partial derivatives of that thing, okay, and set it to be 0, which gives us something. And then take more part and then substitute it. I think I used the implicit method in any ways, because I thought, well, it might be easier, who knows, especially when there are more variables. And so anyway, I got to this point, and then as the book says, at that point for the simpler example, all the equations are 0 when x equal to y equal to z equal to w, and therefore we'll just call that as the maximum. Which gives us x then equal to a quarter to the power 1/3, and then multiply 4 of them will be 4 of them together. Okay, and let's call that done. Next, problem 7. Problem 7, we have to add a condition for the 4 dimensions, which doesn't take much long. So I added the 4 dimensions. Then so you just slap on a bigger triangle, right? The bigger determinant bigger than 0 for relative min, and then for relative max, we'll reverse the first and third inequality. That is, the second and fourth inequality, you can't reverse it because it just all the negatives will cancel out because they have even number of rows or columns. So that's that. Okay, that's problem 7. Next, problem 8. We are going to test problem 7 by 2 very simple examples, which is what I did here, and it does work out. Okay, this one has a relative min, which is also obvious by the look of it, and similar G has a relative max, again by testing all the determinants, 1, 2, and the 2, 3, and 4 determinant. Which turns out to be very simple because this is a very simple example. Just a quick test of the statement the guess we made in problem 7 to see if it works. So it does. And next, let's look at problem 9. What is that? It's some kind of a function, okay, where it has I don't even remember what it is. Maybe I should look at it first. Problem 9 says that show by inspection this thing has a ridge of minimum. That's true, okay? The thing goes up like that. And then none of these relative minimum, then hypothesis 4 is violated. Okay. So then if that's the case, it violates hypothesis 3 of theorem 4 because this thing happened to be 0, okay, and theorem 4 requires this thing to be bigger than 0, okay, in both cases. So that's how it's violated, and yeah, we know that by calculating various second derivatives, which in this case turns into quite short and easy to do. So that is problem 9. So next, let's look at problem 10, where we are proving the necessary condition. In other words, we have to prove that if a form 1 is a positive definite, then these things all are true. All right, so we're proving this direction. Now, in that case, we have okay. So, and we even got some hints. The book the problem gave us hints on how to pull this off. Now the first hint, well, I could have guessed that myself, right? You just plug in x equal to 1, x1 is 1, x2 and 3 are 0. Then very quickly, then you notice that f equals to f11, which is bigger than 0 because f is positive definite. Okay, so you prove that a11 is 0. Now the next step is not as obvious. So I used the hint that we're supposed to plug in, let's see, what I don't even know what that is. Well, anyway, so we plug it in, all right? There might be some garbage here that I didn't scratch out, but doesn't matter. It's still following the hint. The answer is still pretty obvious. So we let x123 equals minus 2, 1, a11, and 0. Now, if you do that, then f equals to this thing, and very soon you solve it. It equals to a11 times that other thing. And what is it? That's exactly the second. That is exactly this thing right here. Okay. So if a11 times that thing is bigger than 0, being that f is positive definite, and a11 we already showed that it is bigger than 0, which means that has to be bigger than 0. So pretty quick, smooth answer. That's that we easily came up with. And then the third, the 3 dimensions, that's when I got into serious trouble. Okay, yeah. Anyway, so I did that, and let's see, I wrote it all out, and I could not get it to work. The point is, we need to prove the f, the big F, okay, with the a31, a32, a33, which and I probably messed up in here, being that I couldn't get it out. It has to be equal to w times triangle, where w is the 2 by 2 determinant. Okay, in other words, the 2 by 2 times the 3 by 3 should I be equal to this. I also have it written down here, and except that I could not get it to come out, and I probably screwed up in here somewhere, and I'll look at it a little later. But I already spent a lot of time in here, and I was so tired, so I decided to use the calculator, and so that I can do this video. And after the video, I'll go look at this some more and see where I screwed up. Okay, why can't I get the thing to come out? So I used the calculator to calculate the both of these things, the first one and the second one. Okay, and you might think, wow, how did you enter all that stuff in the calculator? Well, there's more stuff here than there really is. What happened is, here's what I did. I plugged in, the Wolfram calculator is able to accept variables. Okay, so I let a11 be a, a12 be b, and there are actually only 6 variables in that mess. And then a31 is going to be this relationship, okay? And when you do the math, and which is going to be x1 for us, and a32 is that one. And as you notice, I messed up a little bit, so which means I wasn't able to get the right answer at first, but eventually I found my mistake. It was and was able to get to the end. So anyway, I did all this, and then so f of a1 a31, a32, a33 equals to this thing, which, yeah, I made a bunch of mistakes. But anyway, it's equal to this thing by the time I got out of it. And this is the 2 by 2 determinant, and that's the 3 by 3 determinant. And I know that this equal to that times that because of what happened before. See, before our formula gave us fa11, see, the function gave us f of a11 times the determinant. So in other words, the first number times the 1 by 1 times the 2 by 2. So I suspected that the second function will give us basically the 2 by 2 times where'd it go? The 2 by 2 times the 3 by 3 answer. You see, which is what this is. See, I figured that this thing should ideally give us w times delta. And if it does, we already know that 2 by 2 is positive, and so that we can prove that the delta, the 3 by 3 is positive because f is positive definite. So the trick is just to get these two things to be equal, and for some reason I couldn't do it. I will check to see where I screwed up. I probably messed up a sign or something I just could not get it to come out. Anyway, it was all really confusing. But in any case, I typed it into the calculator, okay? And that made it. So here's how I typed it into this is the expand calculator. In reality, all I did is just write down the word expand in here, and it just expanded it. It just worked in the Wolfram calculator. So it is a really impressive calculator. Anyway, so I typed in that equation here, okay? And to type this equation, here's a tip that if you type something like this into a Wolfram, a big long thing, first type just a few things and then push the equal sign to see if if it spits out something sensible. If it tells you, I don't know what you're talking about, then you need to do something about it, you know, before you type in the entire big long formula and then it says, I don't know what you're talking about, you don't know what's wrong with it either. If you just type in a few terms, then if it says it doesn't know what you're talking about, then you can easily find what's the problem easier. But anyway, so I typed it in. At first, I couldn't get it to understand me, and then I realized that it needs a spacing. That is, like, see, I have a space between B and E. So I put a space there, and it was okay. All right. So remember to put in spacing if you use this thing. Now maybe you're doing better than me and can get all that calculated out the first time nicely and don't have to worry about the calculator. But I was stuck with the calculator because I make way too many mistakes. So hopefully you don't make the mistakes like I do. And anyway, so I used the calculator and I typed all that stuff in, okay, for whatever this is the F, okay, with the rules here where A11 is A, etc., and then typed it all in and have the calculator expanded. And after a while, it was able to do that. Okay, it expanded this thing to which is F. Again, the big F, okay, the positive definite, equal to this thing right here, okay? Then I use the expand calculator again. This is the 2 determinant by times 3 determinant, which end up being this. And when I expanded that, the calculator gave me this thing. And notice, they are exactly the same, term by term, identical in order. Isn't that impressive? Yeah, so then I proved that this is indeed equal to determinant 2, 2 by 2 times 3 by 3, and being that this is positive, right, and this is positive, and that means the 3 by 3 determinant is indeed bigger than 0, and that is the end of this section.